So I will talk about negative moments of the Riemann zeta function, and this is joint work with Hank Bui, who's here. So we've heard a lot about positive moments from sound and from Emma yesterday. Now I want to talk about negative moments, which have been studied less. So I will start with an introduction about positive moments, because I want to contrast what we know about positive moments to what we know about negative moments. So this will be a board talk, and I think I tend to write quite small, so at least that's what my students complain about. So please let me know if I start to write smaller and smaller. Okay, so the two-case moment of zeta, denoted by ik of t, this is the integral we normalize by 1 over t, and that's the integral from 0 to t of zeta of half plus it to the 2k. These moments have a long history. They were introduced by Hardy and Littlewood. In 1916 as a way to study the Lindelof hypothesis. So they noticed that the Lindelof hypothesis, which is the statement that zeta of half plus it, so zeta on the critical line, is bounded by t to the epsilon for any small epsilon. This is equivalent to getting good bounds for all the positive moments. So this is equivalent to saying that ik of t is bounded by t to the epsilon for all integers k. So since then, moments became natural objects of study. And now we have very good conjectures for what these moments are. And we've heard a lot about it on the first day. So this is the work of Keating and Snaith, using these beautiful relationships with random matrix theory. The conjecture is that ik of t is asymptotic to log t to the k squared times some constant ck, which we will write as a product between two factors ak and gk divided by k squared factorial. So the log t to the k squared part, that is not so hard to guess, and we've already seen this discussed in sound talks. So there are two ways that you can see the log t to the k squared. One is trying to write the two-case power of the zeta function in terms of a Dirichlet series and identifying so-called diagonal terms. So here we would look at the sum. If we look at diagonal terms, this would be the sum of dkn squared divided by n, and say n goes up to t. If we look at these kind of sums, we get that this is asymptotic to log t to the k squared times some arithmetic factor ak, which is exactly the ak that is conjectured here. So this is just given in terms of an Euler product. So it's the product over p of 1 minus 1 over p to the k squared times the sum with m from 0 to infinity, gamma of m plus k over m factorial, gamma of k, everything squared times p to the minus m. So this is just a convergent Euler product. So this part, the ak and the log t to the k squared, these are were pretty well understood even before the work of Keating and Snaith. But this factor gk was really not well understood. There were conjectures. We knew what G1 and G2 was. There were conjectures for G3 and G4 due to Conry and Gauche and Conry and Gonek, but nothing beyond that. So Keating and Snaith, we've heard about it, had this idea of modeling the Riemann zeta function by characteristic polynomials of unitary matrices. So if you think of zeta in analogy with the characteristic polynomial of a unitary matrix, say z of u theta, this is the determinant of I minus u times e to the minus theta. then we can think of the zeros of zeta as eigenvalues of these unitary matrices. So we will write them as e to the I theta 1, e to the I theta 2, up to e to the I theta n. Now we need some kind of relationship between t, so we're integrating up to t, and the size of the matrix. So we can get that by saying that the average spacing of zeros which is on the scale of 1 over log t, that should correspond to the average spacing of eigenangles. And we have n eigenvalues, so that should be 2 pi over n. So then log t corresponds to n. So we have this relationship between the integral, the height, and the size of the matrix. So then what they did is they looked at the integral over the unitary group of the characteristic polynomial. Sorry?
The average spacing of 0 should be 2 pi over log t.
Right, yeah. So I mean, I kind of don't care about constants. So it's just log t, which should be of size n. So then if I'm looking at this and I divide by n to the k squared, I take the limit when n goes to infinity. Then Keating and Snaith computed this integral and this limit, and they got this factor gk, which is equal to k squared factorial times the product of j factorial over j plus k factorial with j from 0 to k minus 1. So then the conjecture is that this gk that you get from random matrix theory is exactly the gk that you write in the moment conjecture.
I have a question.
Yeah.
From the previous talk, we just saw that random matrix theory. I mean the GUE and the GUE doesn't exactly match the random matrix theory corresponding to the Riemann zeta function, right? From the previous talk, we just saw that.
So random matrix theory just gives you this gk, so you kind of have to put in the arithmetic factor by hand.
Okay, so there's still another factor, you're saying?
Sorry?
There's still some extra factor apart from the
yes,
gk?
There is this factor ak here, which is an arithmetic factor. It's an Euler product. So random matrix theory doesn't know about primes, so we kind of have to put this arithmetic factor by hand. So that's the next thing that I wanted to mention, and we've seen this in Stan's talk. There's a hybrid model due to Gonek, Keating, and Hughes, where they actually write the Riemann zeta function as a product over primes times a product over zeros, and then that kind of gives you a more natural way to write the conjecture, which includes the AK and the GK factor at the same time, so that you don't have to put this arithmetic factor by hand in the formula. So the hybrid model this is due to Gonek, Hughes, and Keating. So you write the zeta function, zeta of half plus IT. So roughly, this will be a product over primes of size up to x. You have flexibility in how you choose your x of 1 minus p to the minus 1/2 minus IT inverse. And now you also have a product over the zeros. And we're looking at zeros. So gamma n here, the zeros are half plus I gamma n. We're looking at zeros which are close to t within 1 over log x. Here rho denotes the 0, so 1/2 plus I gamma n. And then they have this kind of independence splitting conjecture. If you're looking at the 2kth moment of this, it should be the 2kth moment of the product over the primes times the 2kth moment of the product over the zeros. Now, if you choose x suitably, then you can actually compute 2kth moments of the product over the primes. So this you can compute, and it will give you the AK factor. For this, you use random matrix theory to model this part involving zeros. So use random matrix theory, and this gives you the GK factor. So maybe this is a bit more natural way to come to the same conclusion. And now you have a way in which you can get the AK and the GK at the same time. Now there is yet another conjecture, a more refined conjecture. This is due to a number of people. So it's Conry, Farmer, Keating, Rubinstein, and Snaith. And they use number theoretic heuristic arguments to write down formulas for the moments. This is the so-called recipe. And there's a different approach using multiple Dirichlet series due to Diaconu, Goldfeld, and Hofstein. And they conjecture that the 2kth moment is asymptotic to a polynomial in log t of degree k squared. So this has degree k squared. You can actually write down all the coefficients of this polynomial explicitly, and then you should have some power saving error term. Let's say t to the minus delta for some positive delta. So now in terms of what is known, so the first two moments are known. The first is work of, the second moment is work of Hardy and Littlewood. The second moment is due to Ingham. And later on, Heath-Brown improved Ingham's result and recovered this entire polynomial predicted by this conjecture. And this is all that is known rigorously in terms of asymptotic formulas. So to do, for example, the sixth moment, you need some information about correlations between divisor functions, and we don't really have information about that. So then you can ask what is known in terms of upper bounds and lower bounds. So there are sharp upper bounds. For k between 0 and 2, they are unconditional. So this is work of Heap, Radziwiłł, and Sound. And under the Riemann hypothesis, there are conditional upper bounds for all k. So all positive k. This is work of Sound with an improvement of Harper. So Sound proved that the 2kth moment is bounded by log t to the k squared plus epsilon, and Harper removed the epsilon. And when we talk about negative moments, many of the ideas of proof are inspired by work of Sound and Harper. Now, in terms of lower bounds, there are sharp lower bounds for k greater than or equal to 1, work of Radziwiłł and Sound. For all positive k, there are conditional sharp lower bounds due to Heath-Brown and Ramachandra. And for k between 0 and 1, we've heard from sounds there are sharp lower bounds due to heap and sound. Okay, so quite a lot is known about positive moments. Now, if we want to talk about negative moments, much less is known. So let me introduce the negative moments and tell you what is known in terms of conjectures and what is proven. So for negative moments, we don't even have, there are some conjectures, but you will see where we stand. So we will denote by I minus k of alpha t, the negative 2kth moments. So now, of course, if we're considering negative moments and the zeta function is in the denominator, we need to be slightly away from the critical line. So this will be the integral from 1 to t of zeta of half plus alpha plus it to the minus 2k. Okay, so we introduce this small positive shift here. And here the problem gets more difficult as alpha gets smaller and smaller because we're closer and closer to the critical line. So we're closer and closer to possible zeros of the zeta function. So there are some conjectures due to Gonek.
You will assume Riemann hypothesis.
Yes, so for most results that I will talk about in this part of the proof, we will assume the Riemann hypothesis. So there is this conjecture due to Gonek from 1989. So he predicts the following. So his conjecture takes two forms depending on how big alpha is. So for example, if alpha is big enough, by big enough, we mean that alpha is bigger than say 1 over log t and is less than 1. So the size of the family, this is a continuous family of size t. So that's 1 over log of the conductor. Then the conjecture is that the negative 2kth moment is asymptotic to is of size 1 over alpha to the k squared.
Is this for k an integer?
This is not for k an integer, no.
Any real k?
Any positive k. So this part of the conjecture is somewhat well understood. But now when alpha gets smaller and smaller, it may be less well understood. So Gonek stated his conjecture in the following way. So now if alpha is positive,
Alexandra, you mean alpha is less than half?
it's a half plus alpha.
So wait, in the region of convergence, this is not.
It's not so interesting, exactly. I mean, really, we care about alpha being small. So ideally, alpha goes to 0. If alpha doesn't go to 0, if alpha is of constant size, I think these moments were understood even when Gonek made this conjecture. So now the interesting range is alpha is less than 1 over log t. So here the conjecture is the following. So Gonek predicted that this is of size. So it depends on how big k is. If k is less than 1 over 2, he predicted that this is of size log t to the k squared. Now, if k is equal to 1/2, he predicted that there is a certain logarithmic correction to this formula. So if k is 1/2, he predicted log t to the k squared times log of 1 over alpha log t. And now if k is bigger than 1/2, then he predicts log t to the k squared times alpha log t to the 1 minus 2k. So there are 3 different formulas depending on the size of k. Now, the theme of this conference is relationships with random matrix theory. So you can ask, if we use random matrix theory, what do we get? Do we get conjectures which are consistent with this conjecture of Gonek? And it turns out the answer is not quite. We get some conjectures which partially agree with Gonek's conjecture. So if we use random matrix theory, there was work of Berry and Keating. And later, so the work of Berry and Keating was for negative moments of unitary matrices. There was later work of Forrester and Keating. This is from 2002, 2003. So Forrester and Keating looked at circular beta ensembles for all beta. And there was also work of Fyodorov and Keating for the GOE ensemble. So it turns out that if we focus on this family, this unitary family, it turns out that using random matrix theory approaches, that predicts more jumps. So you already see this kind of transition regime when k is equal to 1/2. There is this logarithmic correction. Actually, what random matrix theory predicts is that there should be extra transition regimes when k is equal to 3/2, 5/2, 7/2, and so on. So in fact, what they noticed is that clusters of zeros tend to have a big effect on these negative moments. So for example, they explain this transition regime here by looking at pairs of zeros which are close together, and those kind of cause this logarithmic correction. But they went further and they said, well, if you look at, say, clusters of 3 zeros close together, what do you get? And it turns out that those start to contribute once you're negative enough, so when k is equal to 3/2. And then if you look at even more clusters of zeros, those have a contribution when k is 5/2, 7/2, and so on. So I will write down a conjecture based on these random matrix theory computations. They have not been written down explicitly in these papers that I've noticed, that I've mentioned, but that's what you would get if you use the same Keating and Snaith approaches. So I will write it in quotes, and if there's any mistake, it's not in these papers, it's me. So when alpha is between 1/log t and 1, then actually the random matrix theory computation agrees with Gonek. So this is not controversial. Now, if alpha is small, then the conjectures agree up to 3/2, and starting with 3/2, they disagree. So we will write it the following way. So now if k is between j minus 1/2 and j plus 1/2, then the conjecture is that this is asymptotic to log t to the k squared times alpha log t to the minus j times 2k minus 1 minus 2k minus j. So this is when k is between j minus 1/2 and j plus 1/2. Okay, so if you're in between half integers, this is the conjecture, and it actually agrees up to 3/2. But when k is equal to a half integer, so if k is j minus 1/2, then you get some extra logarithmic corrections. So it will be log t to the k squared times alpha log t to the minus j times j minus 1. So it's quadratic here. And then we get this log of 1/alpha log t.
Is there some constants?
I will talk about the constants. So in Gonek's conjecture, there was no constants, no constant written down. Of course, in random matrix theory, you don't really get arithmetic factors, but it's not hard to write down a constant. Any questions so far? Well, you're on the critical line, so you have. Yeah, but what do you do about the zeros? If you're on the critical line?
Well, you average it, right? So
Right, but I mean, you have zeros, so you have poles in there.
yeah, it's a bit of
K small. K less than half. And the multiplicity. That's why it's not.
Say something about Gonek motivation.
About Gonek's motivation? Yeah, so Gonek, when alpha is big enough, actually what Gonek did was pretty much the recipe, but the recipe came like 20 years later. When alpha is small, he kind of related these negative moments to discrete negative moments. And then for the discrete negative moments, he again used some Dirichlet series, and so pretty much, again, ideas behind the recipe. But he never stated it in that way. So in fact, using, that's what I wanted to say, if k is an integer, so this conjecture holds for any positive k. If k is an integer, if you look over here, so you're in between ranges, you actually get that the negative kth moment is of size 1 over alpha to the k squared. So it's exactly the same shape as you have in this big range when alpha is bigger than 1 over log t. And in fact, you would get this same conjecture for integer k if you replicate what the recipe does. So I will also talk a little bit later about the ratios conjecture due to Conry, Farmer, and Zirnbauer. So there they use kind of the same ideas behind the recipe to predict positive moments to study ratios. They didn't actually write it down for just negative moments, but it's pretty easy from their work. So if you do that, you actually get a main term of size 1 over alpha to the k squared. So the random matrix theory conjecture is consistent with the recipe. The recipe has the advantage that it also gives you the arithmetic factor. So actually you can refine this conjecture. And you can put in an arithmetic factor here. So it will be some AK. So the arithmetic factor, again, I'll write it with a question mark. It hasn't been written down, but you can do it quite easily. So the AK will be the product over primes of 1 minus 1 over p to the 1 plus 2 alpha to the k squared. And then 1 plus a sum with j from 1 to infinity, mu k of p to the j squared over p to the 1 plus 2 alpha times j. So here, mu k, these are the coefficients of zeta to the minus k. Now, what is known towards these conjectures? So there are lower bounds. Due to Gonek, in the same paper where he made these conjectures, So he proved sharp lower bounds when alpha is bigger than 1 over log t. And he also got sharp lower bounds. Again, this is all conditional on the Riemann hypothesis. He also got sharp lower bounds when alpha is less than 1 over log t and k is less than 1/2. Okay, so he essentially got sharp lower bounds in these ranges, which agree in his conjecture to random matrix theory. Now, when alpha is of size, say, 1 over log t to the big O of 1, where to the left of 1 over log t, and k is greater than or equal to 1/2, then he gets some lower bounds. They are not sharp, but they are off by some powers of log. And this is pretty much all that was known. So now what do we prove? So in joint work with Hang, we proved the following thing. So we are looking at upper bounds, and we get upper bounds. Again, we assume the Riemann hypothesis, and we get upper bounds in various ranges. In some ranges, they are sharp or almost sharp. In some ranges, they are very far from sharp. So when k is small, we go up to 1 over 6. Maybe this 1 over 6 can be improved to 1/2. So when k is less than 1 over 6 and alpha is bigger than 1 over log t, so we're to the right of this line, 1 over log t, we get almost sharp bounds. So we bound the negative to kth moment by log t to the big O of 1. So this big O of 1 here is explicit. I think we get something like 2k squared. It depends on k. And probably with a bit more work, we could get a sharp upper bound. Now, if k is bigger than 1 over 6, the problem is harder. So we would like to be able to go down to 1 over log t. We can't quite do that. So we get almost sharp upper bounds when the shift is bigger than 1 over log t to the 1 over 6k. So we get the same shape of the upper bound, log t to some big O of 1. And we also want to know what happens when alpha is smaller. So for example, if k is bigger than 1 over 6 and alpha is to the left of this point, then what do we get? So we get the following. Let me denote by u the quantity log of 1 over alpha over log t. You can maybe think of this as a constant. So if you are to use some pointwise bound for the zeta function, you would get that I minus k of alpha t is bounded by t to the ku. Now what we do is we shave off a little bit from this trivial bound. So we get t to the ku times some constant, which is an infinite product with m from 1 to infinity of 1 minus 5 to the m over 6 to the m ku. So this is an infinite product, this converges, and it's less than 1. And what the trivial bound would give you in this case is just t to the ku. So we save a little bit over here for small shifts. Are there any questions so far?
Push the board.
Um,
The board up a little. When it's like 1 over log t, why don't you get sort of the log t thing?
Yeah, it's a small technical thing. We could do that. So, I mean, basically, when you do moments of zeta, positive or negative, you have sums over prime powers. And so you have sums over primes and sum over primes squared. And kind of from the way we deal with the prime squared, it introduces this 2k squared instead of k squared. But it's really just, I mean, we could work a bit harder and get the k squared.
Are there potential applications of the lag?
I will talk a little bit about applications later. Other questions?
Yeah, so do you think that there's a limitation to the method in terms of distinguishing between these two conjectures over here? You can't get up to more than one. Right? Conjecture differs when k is bigger than 3 halves and alpha is close to.
Yeah, but I mean, we're over here, k is bigger than 1 over 6, but we're far from 1 over log t. So you need to be to the left of 1 over log t to be able to distinguish between those formulas.
I guess my question is, I think that's a problem with the method. You can't actually get up to 1 over log t.
Yeah, we can go up to 1 over log t.
Did you already say what the trivial bounds would be?
The trivial bound is t to the ku.
Oh, thanks.
Yeah.
Wait, that's the trivial bound using RH or?
Assuming RH. Yeah, yeah. Everything is under RH. Okay, so in fact, for these two cases that I wrote over here, so when k is less than 1 over 6 and alpha is bigger than 1 over log t, and when k is bigger than 1 over 6 but alpha is big enough, we can actually refine these upper bounds to get an asymptotic formula. So that's maybe a corollary. So in cases 1 and 2, actually, in case 1, you can't really go down to 1 over log t. You need alpha to be bigger than some explicit constant ck times log t over log t. So here k is less than 1 over 6. And in this second case, when k is bigger than 1 over 6 and alpha is bigger than 1 over log t to the 1 over 6k, then we actually get asymptotic formulas. So the negative 2 case moment is zeta of 1 plus 2 alpha to the k squared times this arithmetic factor ak that I wrote down before. And we have an error term little of 1. So it happens many times that once you have an upper bound or a sharp upper bound or close to sharp upper bound, then you can actually refine it to get an asymptotic formula. So this is what we do here. Any questions?
In the case of positive moments,
Yeah.
Asymptotic formula is a polynomial of log t. Do you expect some rational function?
Right, so you have like zeta of 1 over 1 plus 2 alpha to the
That would
k
be the
squared.
main term, but maybe there are additional terms.
We can't detect those.
You
Yeah.
can't detect.
Yeah. We are, I mean, we only saved very, very little in the error term, so we're far from detecting any,
Do you expect it? I mean, I would expect that there would be additional.
maybe, I don't know.
Well, I'm sure there are, but you're only going to polynomial integer values of k.
Right. But
you
already
would expect the same.
in the fourth moment, there's a polynomial.
Yeah, no, I mean, I thought you were asking about power savings, lower order terms. Yeah, a polynomial you should expect, yes.
It would be some rational function. It wouldn't be a polynomial.
So in the recipe, there would be no, in the ratios, there'd be no swaps, right? So it would all come from the diagonal.
Yeah, it all comes from the diagram.
Yeah, so you should be, so we can write those down.
Yeah, you can write those down.
Is there an asymptotic like this in the RMG setting?
So in random matrix theory, yes, there are formulas due to Berry, Keating, Forrester, and Keating. So yeah, in random matrix theory, these kind of results are theorems. So not only for negative moments, but also for ratios. And in fact, there are exact formulas in many cases.
That's a geometric factor, right? That's because constant is 1 in the
The constant, I'm not sure if it's 1.
Which constant?
When you compute negative moments?
Constant we talk about? There's a non-trivial constant here.
Yeah, I'm not sure what the constant is. So the question was, what is the constant in random matrix theory?
Arithmetic constant is factors 1.
Right. Yeah, but is there?
There's a non-trivial.
Yeah.
Constant, yeah. It's a hypergeometric function.
So that we don't see here. Okay, so before talking a little bit about the ideas of proof, I just wanted to say that there are somewhat similar results over function fields for the family of quadratic Dirichlet functions. And I also want to talk a little bit about the ratios conjecture, which is a generalization of negative moments. So in some sense, it's combining what we talked about before, positive moments with negative moments. So I will just, so this was a precursor of the ratios conjecture, was a conjecture due to Farmer, where he's looking at ratios of 2 zeta functions over 2 zeta functions. He had a conjecture for that. And it turns out that if you assume that conjecture of Farmer, you can prove the pair correlation conjecture of Montgomery. So that's why people started to care a lot about these ratios. So later on, this was formulated in greater generality by Conry, Farmer, and Zernbauer. So here you're essentially looking, so S is on the critical line, and you're looking at integrals of the form zeta of S plus alpha, zeta of 1 minus S plus beta, divided by zeta of S plus gamma, zeta of 1 minus S plus delta. I won't really write down what the conjecture tells you. It's a bit complicated, but they write down precise formulas with a power saving error term. And they conjecture these kind of formulas for shifts alpha, beta, gamma, delta with real parts less than a quarter. And the shifts in the denominator having real part bigger than 1 over log t. So in some sense, you're to the right of this important line 1 over log t. They also have more general versions where they consider 2k zeta functions here or 2L zeta functions here. And this recipe applies to other families of L functions as well. So it turns out if you do the same kind of heuristic arguments, but now with no zeta functions in the numerator, you can recover these conjectures that I talked about negative moments. So a few applications. Turns out the ratios conjecture has applications to a lot of problems. So I mentioned before that it would imply the pair correlation conjecture. You can also obtain amazing non-vanishing results using the ratios conjecture. So for example, if you look at the family of quadratical functions, Sound showed that more than 7/8 of L1 half chi d are non-vanishing. We expect all of them to be non-vanishing due to a conjecture of Chawla. If you assume GRH, Osduk and Snyder got a 94% of non-vanishing. Assuming the ratios conjecture, you get 100% non-vanishing. You can also do things like compute mollified moments. Compute, for example, lower order terms in the pair correlation of zeros of zeta and so on. So I'm just writing a few of them. So what are some of the ideas in the proof? I will spend the remaining time talking about that. So actually, before talking about the ideas of proof, let me just mention that in random matrix theory, there are theorems for ratios of characteristic polynomials. And this was studied by a lot of people. I'm not really an expert on that, so I might not mention some people. So some of the results were proven by Borodin Strahov, Conry Farmer Zirnbauer, Conry Farmer Snaith. Let me see, I'm missing some people, definitely. Sorry? Bump and Gambard. Thank you, Fyodorov, Strahov, and so on. Okay, so let me talk now about the ideas of proof. So here, we start with the key lemma. So many of the ideas of proof are similar to the work of Sound and Harper for positive moments, but we will need one extra ingredient to deal with some of our cases. So as usual, when we consider upper bounds for moment, we need some inequality for log of zeta. We're considering negative moments here, so we need a lower bound for log of zeta. So we start with an inequality for log of half plus alpha plus IT. This is adapted from work of Carneiro and Tandy. So looking at log of zeta inverse, this is less than or equal to the real part of a sum over the primes of size up to x, and we have flexibility in how we choose this point x. We have some coefficients a of p, you can think of them as being 1, e to the 1/2 plus alpha plus it. Now we have a contribution from zeros, so it's a log t over log x times log of 1 over 1 minus x to the minus alpha. So if you stare at this term a little bit, you can see that this gets worse and worse as alpha gets smaller. And then we can write an error term of size big O of 1 coming from higher powers of primes. So then if we exponentiate this, we get that zeta half plus alpha plus IT to minus 2k, and this will be bounded by the exponential of the sum over the primes times this the exponential of this big term over here. So now we want to approximate the exponential of the sum over the primes by a truncated Taylor series and then hope that we can compute moments over there. So the question is, how do we pick the x? And now we are using this Harper idea where we split the primes into infinitely many intervals. So primes between t to the beta naught, t to the beta 1, up to say t to the beta k. So we will stop when beta k is a small constant. Now I can tell you exactly what the beta are, but I don't think it will be very illuminating. Maybe I will just mention that beta 1 is of size log t over log t. And then we look at small primes. So we look at points t in this set t naught. This will be an exceptional set. So how is this set defined? Well, this is a set where the contribution from the first primes, from the small primes, is bigger than some threshold that we need to pick. Say beta 1 to the minus d. D is a constant that we will pick at the end. It's between 1/2 and 1. We have to optimize the choice of d. So it doesn't happen too often that the small primes have a big contribution. So basically what we want to do is the following. So we will show that the measure of this exceptional set is small. And this will give us some saving over the trivial bound. So if we're looking at the integral over t naught of zeta to the minus 2k dt, then if we use, for example, Cauchy-Schwarz or Holder, this is bounded by the moment over the whole interval 0 to t of zeta to the minus 4k to the 1/2 times the measure of t naught to the 1/2. So we need to show that the measure of t naught is small, and then we need some kind of bound for this 4kth moment here. So we don't really have an a priori bound for the negative moments. So all we can do at this first step is just use the trivial bound, the pointwise bound for zeta, and hope that we can gain a little bit over the trivial bound from here. So use pointwise bound. So for example, in Harper's work on positive moments, when he has to bound the contribution from the exceptional set, he also uses Cauchy-Schwarz, but he sounds almost sharp bounds. So he gets a much better error term there. Then we move on to the next interval. So these are points t, such that, say, the real part of the primes on the jth interval is small. So these are well behaved for, say, j up to some point r, but the contribution on the r+1 interval is big. But the contribution on the r+1 interval is big. Then what we do is, in that key lemma over there, we choose x is t to the beta r. And then for the integral over TR, so zeta to the minus 2k dt, for the primes in the intervals up to R, we basically approximated the exponential of the sum over the primes by a truncated Taylor series. So this will be less than the integral. And here, ELJ, this means that it's the truncated Taylor series for the exponential, truncated at some point LJ, which you have to choose carefully. And we want to bound this contribution on TR, so we have to make use of the fact that the contribution on the R plus 1 interval is big. So we multiply by beta R plus 1 times PR plus 1 of T. And we have to raise it to some even power, say SR plus 1. Again, don't worry too much about these parameters. We will have to choose them in a suitable way. So now the point is that if you choose the parameters appropriately, then that will actually be a Dirichlet polynomial of reasonable length, and you will be able to compute moments of that. Okay, so you can compute moments. The length will be T to the sum of beta j Lj. So this is Lj is the point where we truncate in the Taylor series. And then we get to the end, to the set of points T, for which all the contributions are well behaved. And this term is okay. So this is bounded by log T to the big O of 1. So if we run this argument similar to Harper's, we will get a little bit of saving from here. So we will end up with an upper bound of the form T to the KU times some YK. This is a constant which is less than 1. It depends on K, and it gets worse with K. So for example, you can think of it, it's not exactly that, but you can think of it as being roughly 1 over 1 minus 6KU. So we saved a little bit, and then the idea is that you want to iterate this process. So now you go back to the exceptional set. You have to define your parameters differently. So now you split the primes into different intervals, different boxes. And you get to this step, so you have to make sure that the measure of the exceptional set is small. You bound this by zeta to the minus 4k. And now instead of using the pointwise bound, we will plug in this improved bound. And we will save a little bit more over this first bound. So if you do that again, you will end up with a bound of the form T to the KU YK times Y2K. So now you're saving a little bit over this second bound, but not as much as before. And you iterate this process. And if you do that, you will end up with this constant T to the KU times YK, Y2K, Y2 to the 2K, dot Y to the 2M times K. And that will converge to that constant that I wrote before. So of course, we're not saving that much over the trivial bound here. For bigger shifts or small k, we do obtain almost sharp bounds. So it would be interesting to maybe obtain some sharper bounds in these regions where we're closer to the critical line. So maybe one idea is that we could maybe try to exclude some set of bad points in the interval and hope that we can maybe, for a thinner set, we can prove some kind of sharper bounds. And ideally, we would like to be able to detect these transition points predicted by random matrix theory. So I will stop here. Thank you.
further questions?
Yeah, you said that there's some technical problem from the square of the primes, and I noticed you didn't write that in that formula. or-
Yeah,
Yeah.
that's why it's not, yeah, you have to include the squares. So basically for the squares, we do what we did for cubic L functions. We use Cauchy force to separate the primes and the prime
Yeah.
square, but that gives you a loss in the power.
Yeah, because then you cannot use a good bound to start with, so everything is very tight.
Yeah, well, I mean, over here, we're pretty far from a good bound anyway. But yeah, that introduces a small loss. So if you are to deal with the primes and the prime square at the same time, then you should get sharp bounds.
Okay.
Yeah, but I mean, already it's a bit technical, so we didn't really
Yeah,
work
because
on
an
it.
Harper, it doesn't have this induction step, of course. That you
Yeah,
need,
yeah.
Because you get such a, so you can do the square. I can imagine it. gets
Yeah,
very
yeah,
difficult.
Harper works with the squares, with the prime squares and the
At the
primes
same time.
together.
Yeah, but it has no induction.
He has no induction.
So I guess you can translate the result in terms of large prediction of log theta to the negative. So what kind of field does that imply?
I don't know. We haven't thought about that.
Well, then let's thank Alexandra.